Hello everyone. We are waiting participants who are late, and we will start at 10:35. Okay, let's start. Hello everyone. My name is Can Dugan. I am visiting assistant professor doctor at the Department of Computer Engineering in Middle East Technical University, and I'm also assistant professor doctor at the Department of Computer Engineering in Artmich University. Today is the second day of our training, namely parallel computing on GPUs with CUDA. This training is organized by EuroCC project, TÜBİTAK Ulakbin, Sabancı University and Middle East Technical University. Okay, sorry. First of all, I would like to give a summary of the topics that I will tell you today. The first topic, which is also the first session, is debugging and profiling performance of your applications. I will tell you the debuggers, CUDA memcheck and CUDA GDB, and also the profiler MVProf. And then in the second session, I will mention to the performance optimization of your algorithms and the efficiency concept in CUDA programming. And the examples are, the problems are the coalesced access to the global memory. The second one is the warp divergence. The third issue is device occupancy and streaming multiprocessor efficiency. And the last one, an example about efficient parallel reduction algorithm. And in the third session today, I will show you some of the libraries such as Trust library, CAP library, and I will compare their parallel reduction algorithms. And the second topic is the remaining issues, such that use of CUDA mapset, the proper use of CUDA mapset, and the initializing cost of the states of the random number generators, and the L1 cache used in Tesla K40 board. And in the last session, I will show you a sample and an application that we did in the past, that is memory coalescing implementation of Metropolis resampling. I will tell you our proposed coalesced variants of Metropolis resampling, and I will compare them in terms of bias, mean square error, and the target tracking performance. Then we conclude the training today. Okay, let's start with our first session. Debugging and performance, profiling performance. First of all, I would like to tell you the board I used in the experiments. The specifications are important. For example, this is Tesla K40 board. It has Kepler architecture. the number of streaming multiprocessor is 15. This is also important. And the segment size is 128 bytes. This is also important. I will remind you again in the following sessions about the specifications of the SK40. And there are some constraints or limitations on the hardware. These are at most 2048 threads can be active in a stream multiprocessor. At most 16 blocks can be active in streaming multiprocessor. This is also important. And at most 1024 threads can be created in a block. These limitations are also important. Let's start with debugging tools. There are mainly 3 debugging tools. These are CUDA memcheck, CUDA GDB, and Insight. I will tell you first 2 of them, CUDA memcheck and CUDA GDB today. Let's continue with CUDA memcheck. It is used to detect memory access errors, and it is used to detect runtime errors. It is installed as part of the CUDA toolkit, and it is supported on all CUDA supported platforms such as Windows, Linux, Android, and is supported on all CUDA capable GPUs with SM version 3.5 and above, but it is not supported on virtual GPUs. And this is the website of CUDA memcheck. You can get detailed information through this website. And in CUDA memcheck tool, there are 4 main tools in CUDA memcheck. These are the memcheck tool. It is used for memory access error, detecting memory access error, and leak detection. The second one is race check. It is used for shared memory data access. The third one is init check. It is used for detecting uninitialized device global memory access. And the fourth one, sync check. It is used for thread synchronization detection. Okay, let's continue with the first tool of CUDA memcheck, which is memcheck tool. It is a runtime error detection tool for CUDA applications. There are some error types, and this tool tries to detect them. Let's look at the errors here. The first one is memory access error. This is occurred because of the out of bounds or misaligned access to the memory. This error occurred because of out of bounds and misaligned accesses to memory. This memory can be a global memory location, local memory location, shared memory location, or a global atomic access. As the second error is hardware exception. It is reported by hardware error reporting mechanism. The third one is malloc-free errors. It arises because of the incorrect use of malloc or free. And the fourth one is memory leaks error. It is about the memory locations which are created in device memory by using CUDA malloc or malloc functions, and it has not been freed. After your program exit, it still has not been freed. This is memory leaks error. I will show you examples about them. And the last one is CUDA API errors. When a CUDA API call returns a failure in your application. Let's look at the examples. Let's start with the first one. memory access error. Here is a simple example. We have an array GPU in device which is created in device memory, a GPU. We create it with 3 elements here. Then we call the function, relevant function, and we call CUDA free. Here, inside the run access error, there are some message here. And we have a kernel. Memory access error kernel here. Start with global keyword. So this is a kernel on the GPU. And it takes our array as an input. Here we are trying to assign a value to the location of one of the location of this array. The first example is about out of bounds error. That means we exit the last item of the array. Here we have 3 elements in our array. And in here, inside the kernel, 100 is tried to store in the 4th element of array, global array here. By adding 3 to the address of array, we are trying to access to the 4th element of the array. But our array consists of 3 elements, so we get out of bounds error. And we create here our kernel with a single thread and single block in this example. Okay. With this command, we can compile and we can run. When we run our program, okay, let's focus to this printf first. Here there is this is the first printf. It prints running memory access error kernel. Second printf prints run memory access error kernel. The third printf try to print the last error that is arised in CUDA runtime here. Then in the fourth printf, we call CUDA device synchronize API, as you see. So the host is waiting until the kernel terminates this command. Remember from yesterday, CUDA device synchronize, and if there occurs an error, it will be printed in the fourth printf. And in the last printf, we are trying to print again the current CUDA error. Even if we face with a problem here in out of bounds error, we cannot here detect in the output of error. There is no error in the output. As you see, no error, but we have out of bounds error, but we cannot handle it in the regular run of our application. I will tell you the reason. Let's run our application. Let's run this code. Sorry, just a minute. I'm sorry. Okay, let's run it with our memcheck tool, CUDA memcheck, and this is the name of our application. Let's examine the output of our program. Here we face a out of bound problem here. Let's look at the information in this output. Here, as you see that global, since our variable is a global variable, this is shown here, and it is a write operation to the global memory, and the number of bytes of the memory location is 4 bytes. Since it is an integer type, it takes 4 bytes. And in the second line, here the name of kernel is given, memory access error. And this is in the left of the kernel name. This is the PC number, PC number of the instruction. And in the third line, the information of the current thread. This is the first thread, as you see, and information of the current block, as you see that this is the first block. And in the last line, the address of the memory location is given, and the message of the error is given, as you see. Here in our in the third printf, we must receive an error, but we didn't get it, because in order to capture the error, the CUDA device synchronized must be used first. If you don't use CUDA device synchronized, you cannot capture the error. So here we also receive the following information. They are here about unspecified launch failure. The first one is about CUDA device synchronized API. The second one is about CUDA get lost error API, and the third one is about CUDA free. Let me show you again. Here we get the CUDA launch error with CUDA device here first. Then with the second get lost error API, we get another launch failure, and with CUDA free we get another launch failure message. But for the first one, for the first CUDA get lost error, we didn't receive an error even if we use CUDA map check, because we haven't called the CUDA device synchronization function yet. Okay, because when we call CUDA device synchronize, that error is detected and captured. Then for the following APIs, we get launch failure error, because our kernel terminates unexpectedly. Our program may not be terminate immediately, but the kernel terminate or exit unexpectedly. So we will get such launch failure errors. The second error type is misaligned access error. Here, now I replace the contents of kernel with the current one, and trying to assign 100 again to a memory location of our array A. In this case, why we get an error? Because first we convert the address of A to a car array, so we get the address, and when we add a value, we add this value to the next memory byte of the addresses. For example, here when we add 1, that means we are trying to access to the second byte of first element of A. Each element of A consists of 4 bytes, because they are integer types, and we are accessing each byte of a memory location or an element of array. Here, this is the first element, and we are trying to access to the second byte. of the first element with this command, and we get this error because it is not a valid access, because this must be 4 bytes, because each element consists of 4 bytes. In order to access to another element here, we must use a number, use an index which is multiple of 4. And here again we got we received an unspecified launch failure for CUDA device synchronize, CUDA get last error, CUDA free. Sorry, here the first one is about CUDA device synchronize. The second error is the second CUDA get last error, and the third error is for CUDA free. But for the first CUDA get last error, we didn't receive an error message because we haven't called the CUDA device synchronize yet. And the another error type is malloc free error. Here we have a kernel again. We allocate a new device memory, device heap memory with malloc inside the CUDA kernel, and it has 10 elements here. And we create 2 threads for our kernel. And here we free the array. After freeing the array, we again try to free it. And we will get an error. This is the output of CUDA memcheck. Here we encountered with double free error. This is the name of the error. And the second line is the PC of the instruction. The third one is the thread information. The ID is 1, so this is the second thread in first block. And the fourth line is about the address of the memory location. And for the other threads, we again get an error, same error. The only differences here is about the thread ID. Now thread ID is 0, it is the first thread, and the address of the memory location is different because it creates its own array inside the kernel. And again, when we call CUDA device synchronize at the end, we will get CUDA launch failure error with CUDA device synchronize API. And okay, the another issue about malloc free error is about malloc. Again, we create a device heap memory with 10 elements. We increase the address of array by adding 1. We get the address of second elements of the array. Now we have the address of the second element, and we are trying to free it. Again, we create 2 threads for our kernel, but we get another error here because of free. The error is we are trying to free the pointer that was not returned by malloc. What that means, here we create an array and we use malloc, create a device memory location, and malloc returns that information to our array. But when we change the address of this array by setting the address of the second element of array, here we changed its address, but the second element as a pointer. So think about that it's a pointer. The second element is not returned by malloc. So we get an error. Here we get invalid pointer to free error. This is for the second thread. Again, we get the same error for the first thread, invalid pointer to free. Again, we get unspecified launch failure for the CUDA device synchronized. Okay, the second element of array, now the current address is the address of second element is not returned by malloc, but the first one here returned by malloc. That is the region. Okay, let's continue with the leak errors of memory access error. We must use this leak check full flag in order to capture them. Here we again a simple kernel. We create a device array with 3 elements. We call this kernel. Then we reset the device after completing the kernel. We call CUDA device reset, and we get a leak error. Why? Because we didn't here. We don't free the allocated memory locations here with CUDA malloc. We allocate locations in the device memory, but we don't free before calling CUDA device reset function. This CUDA device reset function or API is used to destroy the CUDA context. When we call it, the CUDA content is destroyed. All of the pointers, all of the variables, or etc. will be destroyed after calling the CUDA device reset. So we cannot reach this pointer after CUDA device reset, and since we don't free it before CUDA device reset, a leak error occurred. But we cannot handle it or check it via regular run of your algorithm, so you need to use CUDA mem check and leak check full flag. Let's look at the output of CUDA mem check here. Leaked 12 bytes at this address in one allocation. Since we have 3 elements and it is an integer type, so we created 12 bytes in the device memory and we did not free it. And it is given in the output of the CUDA mem check. Okay, let's continue with another tool of CUDA mem check. It is init check tool. Init check tool is a runtime uninitialized device global memory access detector. So it detects the uninitialized device global memory access, and it detects uninitialized device global memory via device side drives, CUDA mem CPI API call, or CUDA mem set API call. And this tool only supports detecting accesses to the device global memory, only supposed to access device global memory, and you must use tool init check flag, tool init check. So at first you must run CUDA mem check to be sure that your application is free of memory access errors. So you must be sure about free of memory access errors. Then you must run init check tool. Okay, let's examine our example, simple example again. we have a kernel memset corridor. It takes a device array, device pointer, and we add thread ID to this array. Let's look at our main function. We have a global variable and we create here 8 elements for our array. We create 8 elements, and with CUDA map set we set 0, and here this is the third option, third parameter in terms of bytes, so we send 8 bytes here. Then we call our kernel by creating 8 threads here, one block, 8 threads. We call our kernel, and each thread perform this operation. Then we call CUDA device synchronize, then CUDA free GPU, but we get an error in uninitialized memory access error. Why? Because this parameter should be in terms of bytes. When we set it to 8, that means we set only the first two first two elements of the array. So we set first two elements of the array to 0, but for the remaining ones, 6 elements left, they are still uninitialized. So when we try to access it inside the kernel, we will get this error because the last 6 ones still are uninitialized. Here, these are the output of the CUDA mem check. As you see that global and memory of size 4, and the kernel name, thread information here, the last thread. Then you see that the 7 thread, 6 thread, 5th, 4th, and 3rd thread returns an error because they are still uninitialized. How can we overcome this problem? In CUDA mem set, for the third parameter, if we replace 8 with 32, since each element takes 4 bytes and we have 8 elements, in total we must enter 32 bytes for the third parameter of the CUDA mem set. Okay, we conclude CUDA mem check tool now, and let's continue with another debugging tool is CUDA GDB tool. Okay, CUDA GDB is the NVIDIA tool for debugging CUDA applications on Linux and QNX, and it is the extension of GDB, and it supports debugging C, C++, and Fortran CUDA applications. And CUDA GDB allows the users to set breakpoints to single-step CUDA applications, to inspect and modify the memory, to inspect and modify the variables of any given thread running on that way. I will show you examples about them. And this is the website of CUDA GDB. You can get more detailed information through this website. Let's start our example first. Here we have a kernel. The name is the kernel vector at name of the kernel. It takes 3 pointer array, and a vector addition performs. We calculate the global thread ID. I think you learned yesterday. This is the global thread ID, and each thread trying to access by using its global ID. So the operations are coalesced, and addition is performed. Here, this is the size of the arrays to over 15 here. And we create 3 host arrays, we create 3 device arrays, and we set the number of blocks to 1024. And we set the number of blocks is the size divided by 1024. And we initialized A and B. Yes, for the A starting from 1 up to the size. For the B starting from 2 up to the size plus 1. Then we copy the contents of host arrays to the GP array. Then we call our vector called kernel, and then called CUDA device synchronize, and then we call the output of the C to the host array, C host, and we check the error. We perform the error checking here. Then we free all of our arrays. So in order to use CUDA GDB, you must compile it with -G and -G options. And these options force -O0 compilations. That means there will be very limited optimizations in our code. And this again flex makes the compiler include debug information in the executable. And -G is for host debugging, -G is for device debugging. Okay, let's start our debugger. This is the command line commands and outputs. I copied them from the command line. I will show you here. In order to start debugger, you must enter CUDA GDB command here, as you see, and write your kernel application name here. Then once enter, your debugger is started. First, it is better to set the breakpoints. Let's set the first breakpoint to main function by using the name of function here. We set first breakpoint to the main function. Then let's set the second breakpoint by using the kernel name here, vector add. So we set the second breakpoint to the vector add kernel, and we set the third breakpoint. We set the third breakpoints to line 9. Now we are entering the line information here, line number. So we set the breakpoints to the line 9. Then when we enter run, our application starts inside the debugger. When we enter, we will get this output here. We are now waiting in the first breakpoint, which is the main function. The breakpoint in the main function. Okay. Then when we enter continue, our execution also continue. We advance the execution. And here the current focus of debugger given here as an information. Now we are in the first thread of first block of first verb. Our focus now is in the first thread of first block in first verb. Now we are in line 7. Then we press continue. We are now in line 7 here. When we enter info command, info CUDA command, you will get information here. Info CUDA, when we enter info CUDA threads, we will get information about the threads. Let's look at the information. The blocks, the IDs of blocks starts from 0 up to the 29. We have 30 blocks, so the ID starts from 0 up to 29, and we have 1024 threads on each block, so the threads IDs starts from 0 up to 1023. Why we have the total number of threads is 30,720. How can we obtain this one? We have 15 string streaming master processor, remember that. And at most we can create 2048, sorry, at most 2048 threads can be active in an SMX. So when we multiply them, we will get here this number. At most 30,720 threads can be active at a time in our board. Then when we enter info CUDA device here, we get the information about the devices. Since there are two boards in my hardware, one of them is tester K40, the second one is tester K20, you will get the information about them. And again, we can also get the information of kernels by enter info CUDA kernels here. We have a single kernel in our application, vector add, and the block dimension is 1024, and the number of blocks created here is 32. This is the information of kernels. And we can check current focus, and we can switch the focus to another thread. I will show them. First, if you want to check the current focus, by entering CUDA, device SM, verb, lane, block, and thread. And you will see their values here. Block is 0, so this is the first block. Thread is 0, so this is the first thread. Device is 0, so this is tester K14. Streaming multiprocessor is 14, so this is the last streaming multiprocessor. We are in the last streaming multiprocessor, and verb is 0, so it is the first verb. And lane is 0. Lane is the ID of resident thread in the verb, so this is the first resident thread in the first verb. We can also print the values of variables. This is built-in variable block dim. Block dim gives us the block information of the dimension of the blocks. When we print it here, it has three-dimensional information. So the first one is 1024, the second one is 1, the third one is 1. So it is 1D block, and the number of threads is 1024. You can also print the current thread IDs of the current thread in the focus. So since it is the first thread, all of the parameters are 0. We can also print the value of the array. We are printing the second value of the second element of array, which is 2. When we want to print the value of TID here, we get this output, optimized out. Why? Because this line 7 has not been executed yet. We are now in line 7. Remember that here, when we enter continue, we jump to line 7. We are still in line 7 because we do not enter continue again, but it is not executed yet. So we cannot get the output of TID. Then when we enter next, that instruction is executed, and our debugger jumps to the line 8. Now we can print the value of TID. Now the debugger is now in line 8. Here, when we print TID, now we get the proper output, as you see. because line 7 is executed. And we are now in line 8, don't forget. We can also print again any values of B, the sixth element of B, which is 7. We can also print by using TID as the index. Since it is 0, global thread ID of the current focus is 0, so it prints 1. And when we print the value of C, we get 0. It is not a proper output because the instruction in line 8 has not executed yet. Okay, the next issue is we can switch the current focus to another thread. How can we do it here? Before that one, I would like to tell you the coordinates of the focus. There are 2 coordinates of the focus. The first one is software coordinates of the focus. These are thread, block, and kernel. These are software concepts in CUDA. And the hardware coordinates of the focus are lane, warp, streaming multiprocessor, and device. These are the hardware constraints. And these are hardware concepts. Lane is a physical part of physical warp. Warp also is physical. And streaming multiprocessor also physical, and device also physical concepts. And when we want to switch the focus, either you must use either software coordinates or hardware coordinates, but you cannot combine them. You cannot combine and you cannot use together, otherwise you will get error. Okay, let's look at the focusing to the switching focus operation here. Again, by entering CUDA and the information of here, we use software coordinates. We must set the information of the software coordinates, set the kernel to 0, set the first block here, and 36 threads of first block. So the thread local thread ID is 35 here. So we switch the focus to this one. Again, this is the thread of second warp here, as you see, warp 1, because the ID of thread is 35, but in a warp 32 threads reside in a warp. So when exceeding the 31, that thread will belong to second warp here. And the lane information of this thread in second warp is 3. So that means this is the 4th physical thread in second warp. And our debugger jumps to line 7 here. Be careful. When we switch the focus, debugger jumps to line 7. We can also switch the focus by using hardware constraints here. CUDA device 0, we set the device as 0. We set the streaming multiprocessor to 13. The ID is 13, that means this is 14th streaming multiprocessor. And second warp, and 5th thread, physical thread of second warp. So we switch it here. So as you see that now the thread ID becomes 36. So we switch to the next thread of the previous one, previous focus, as you see. And of course, lane information becomes 4. Again, debugger jumps to line 7. And when we enter the next command here, the line 7 is executed. And the debugger jumps to line 8. When we print thread ID, global thread ID. This is, we get 1060 because here we are in the second block. So the global ID of the thread of second block starts from 1024, and by adding the local thread ID 36 here, we get 1060 as the global thread ID of the current focus. When we enter again next, the line 8 is executed. Now we are waiting in this third breakpoint, which is 9. Now we are in the line 9, the third breakpoint. When we print CTID, we will get this error in line 9 because TID is destroyed. It is a register value inside the kernel. So TID is destroyed. So we cannot use it as the index. But since RAC is alive, we can access by using a constant index value. When we enter here 1060, we get our expected output, as you see. And you can also print the built-in variables of the kernels, such as block time, block IDX, thread IDX. So we can also get the global ID by using this combination, because these built-in variables are still alive for the kernel. But the TID, which is stored in register, is not alive, has already been destroyed. This is important. Then, in order to exit your program normally and exit from CUDA debugger, first you must delete breakpoints. By entering delete breakpoints, and by entering Y, we delete all of them. Then when we enter continue, our program exit normally. Of course, there is another way to exit your program normally. Instead of using delete breakpoints, if you use disable command here, then your program again exit normally. There are notes here. A disable command prevents hitting the breakpoint by additional threads. So all of the threads are trying to hit the breakpoints, and we can only manage the current focus, current one, right? And we can switch the focus and access to another one, another threads, and then the following threads will hit the breakpoints and so on. If you enter disable, the threads that hasn't hit the breakpoint yet will be disabled. So only the current threads are active, and when their job is finished, your program exits normally. So disable command prevents the waiting threads to hit the breakpoint for the future operations, and your program exits normally. And kill command also, or pressing Ctrl+C, kill your application instantly. And the third debugger is Insight, but I will not go over in today. It provides debugging visually. There are two types of environment: NVIDIA Insight Visual Studio Edition and NVIDIA Insight Eclipse Edition. You can get detailed information via these websites. Okay, okay, let's continue with profiling. Profiling tools enable you to understand and optimize the performance of your CUDA applications. Some of the CUDA profiling tools are Visual Profiler and MVProf. The Visual Profiler allows you to visualize and optimize the performance of your application, and it displays a timeline of your application's activity and analyzes your application to detect potential performance bottlenecks. And a standalone version of it is NVVP. The MVProf enables you to collect and view profiling data from the command line. I will tell you MVProf today. You can get detailed information via this website. Okay, let's continue with MVProf. It enables you to collect and view profiling data from the command line, and enables the collection of a timeline of CUDA-related activities on both CPU and GPU. These activities can be kernel executions, can be memory transfers, memory set or CUDA API calls, or events or metrics for CUDA kernels. And how can we run MVProf with this one? MVProf command, and there are options, application name and application arguments. Let's look at some of the options. The first one is query events. These options help us to list all the events available on the device, and the query metrics help us to list all the metrics available on the device. And another option is print API summary. Print a summary of CUDA runtime or driver API calls, and print API trace, print CUDA runtime and driver API trace. I will show you examples about them. Another option is print GPU summary. Print a summary of the activities on the GPU, including CUDA kernels and memcpy, memset APIs. So it prints a summary of the activities. Print GPU trace prints individual kernel invocations, including CUDA memcpy and memsets, and sort them in chronological order. So individual kernel invocations are printed and sorted in chronological order. And in event metric profiling mode, it shows events metrics for each kernel invocation. And log file option used for sending all output to a specified file or one of the standard channels. Okay, there are some profiling modes in MVProf. These are mainly 4 types of mode. The first one is summary mode. It is default operating mode, and it outputs a single result line for each kernel function and each type of CUDA memory set operation. I will show you example. GPU trace and API trace modes. GPU trace mode provides a timeline of all activities taking place on the GPU in chronological order. API trace mode shows the timeline of all CUDA runtime and driver API calls invoked on the host in chronological order. And events metric summary mode. Events or metrics are profiled across all kernel executions. Event and metric trace mode, event and metric values are shown for each kernel execution. Let's look at our example code before showing examples about them. We have already a kernel named vector add, and we define another kernel here, vector sub, and it does the vector subtraction. Similar to vector addition, only the operator differs. It does subtraction. Again, we have 3 arrays, host array and GPU array. We set the number of blocks to 1024. We set the number of blocks to size is divided by 1024. We initialized A and B, and save the value to the device memory. And first we call vector addition kernel, then we call vector subtraction kernel, then we free the arrays, and so on. Okay. As I told you before, the summary mode is the default mode. When we run mvprof by entering mvprof and application name, we will get this output. Here, first the memory operations, the information of memory operations are given. There are CUDA mem CPI operations from host to device. Remember here we have four CUDA mem CPI operations. The first two from host to device, we copy the values from host to device. In the third one, we copy the result from device to host. In the fourth one, we copy the array from device to host. So two copy operation from host to device, two copy operation from device to host. As you see here, in the first line, two copy operation from host to device, and these are the execution times of it, average, minimum, maximum. And this is the number of calls. We have two mem CPI operation for host to device, and in the second line here, memory operation from device to host, as you see, and execution times and number of calls. Again, we have two copy operation from device to host. And we have vector addition kernel, we call it once. We have vector sub kernel, we call it once, and these are the execution times. And in the second table, these are the API calls. CUDA Monologue, for example, is called 3 times, and these are the execution information. CUDA mem CPI was called 4 times, CUDA free called 3 times, and so on. These are the information of API. So this is summary mode. If we in summary mode, if we print this flag, print GPU summary, it only prints the information of CUDA kernels, CUDA mem CPI, and CUDA memsep operations. Here, same information, we filter it by using this flag. If you use this flag, print API summary, it will list the information of API calls. Now, again, we filter the result, same result, but we filter it by using this option. If you use print, these are the example of summary mode. Now I will start to the second mode, GPU trace and API trace mode. If here use print GPU trace flag in GPU trace mode, the information, all of the individual calls, the information of the individual calls is given here. Remember that here there is a single line for all of the memory copy operations from host to device, and there is a single line for the memory copy operation from device to host. But here for we get all information of each call here. For example, the first call of memory operation from host to device, the information of second call of memory copy operation from host to device. Similarly, for the memory copy operation from device to host, they are also given in a separate way, and this is in chronological order. So this one is called first, then this one called second, then vector kernel is called third, and so on. So the chronological order. And if we replace this flag with print API trace, we will get individual information of all of the APIs. Here, these are the APIs. We get them individually. Since here, for the second one, there are 166 calls. I cannot show them. I cannot show all of them here because it does not fit to the screen. So I crop it here. So the APIs are printed individually. And the third mode is event metric summary mode. Let's look. Sorry, event metric mode. Okay. Let's look at the definition of event and metric. Event is a countable activity, action, or occurrence on a device and collected during kernel execution. So they are collected during the kernel execution. They can be an countable activity, such as kernels or CUDA memory copy, or action, or occurrence. Metrics is the statistic of an application that is calculated from one or more events. So the metric is calculated from one or more events by using one or more events, and it gives us an statistic for an application. I told you query events and query metrics options before. Let's look at example for event metric summary mode. Now we are in summary mode. In this example here, I use the same example, this one, based on this one. I run them with the corresponding event and metric. Let's look at the event. Event is warps launch. This event, warps launch event, gives us number of warps launch in that application, and GLD transactions gives us the number of global memory load transactions. Remember that the size is 2/15. Okay, 2/15. Okay, when we enter, we will get this output. First, the values of events. For the vector addition kernel, the number of warps launched is 1024. Since we have our data size is 2/15, and the number of threads in the block is 1024, so we will since a warp consists of 32 threads and we have 2/15 threads in total, so there are 1024 warps that run on the hardware. So this is the information of that one, because we have we have 1024 warps when the data size is 2/15. And here GLD transaction, since GLD transaction count, this one I will show you. GLD transaction count the number of transactions for reading A, number of transactions for reading B, the total number of transactions for reading A, the total number of transactions for reading B. Each warp, since these are coalesced access, each warp read A one time, one transaction, Each warp reads B in one transaction. Since we have 1024 warps, so the total number of reading A is 1024. The total number of transaction and reading B is 1024. So in total, it is 2048. Here, as you see, for both kernel, vector red and vector stack. Okay. This is event metric summary mode. Now the third mode is event metric trace mode. In summary mode, aggregate mode is on in default, and streaming multiprocessor specific events are collected across all streaming multiprocessors on the GPU and are shown as a single result. In trace mode, by specifying aggregate mode as of, the values of the events of each streaming multiprocessor are shown separately. So the result of event or metric are shown separately for each streaming multiprocessor in event metric trace mode. And these are some of the metrics. I will use them on the following examples. I will tell them. Let's look at them briefly. The first metric is L1 cache global hit rate. That is the hit rate in L1 cache for global loads. GLD transactions is the number of global memory load transactions, and GLD transactions per request is the average number of global memory load transactions performed for each global memory load. I will tell them again. And SM efficiency is the percentage of time at least one warp is active on a multiprocessor average over all multiprocessors on the GPU. And achieved occupancy is the ratio of the average active warps per active cycle to the maximum number of warps supported on a multiprocessor, and the warp execution efficiency is the ratio of the average active warps per warp to the maximum number of threads per warp supported on a multiprocessor expressed as percentage. I will tell them again on the following lectures, following sessions. And this is the website of the list of all metrics. You can check them through this website. As a summary, I told you debuggers such as CUDA memcheck and CUDA GDB and providers NVProof. These are the references that I used. Okay, let's have a 10-minute break, then continue. Okay, hello again. Let's start to the second session and new topic today. Performance optimization and efficiency. I would like to remind you the specification of the board that are used in our experiments. These are the number of streaming master processor, which is 15. This is important. The number of the segment size, number of size in, of segment is 128 bytes. This is also important. And the limitations, maximum 2048 threads can be active in an SMX. And warp size is 32 is also important. And we can we can create 1024 threads in a block. This is also important. And in an SMX, maximum 16 blocks can be active in an SMX. So we will need all of this information on our experiments. First, I will show you the issue about memory coalesced access to the global memory. And then the second issue is warp divergence. And the third one is device occupancy and streaming multiprocessor efficiency. And then I will show you an efficient parallel reduction algorithm, which was proposed by Mark Harris from NVIDIA Development Department. And let's start with coalesced access to the global memory. So, reading from or writing to global memory performs segment by segment. That means the threads in a warp are physically related to each other. So a warp completes its instruction when all the threads in the warp complete that instruction. This is important. The warps are physically related to each other. So a warp run its instruction. It is completed when all the threads in the warp complete that instruction. In global memory operations, if the threads in the warp access to the different segments of the global memory, the operations become serial. And this is an illustration of non-coalesced access to the global memory. Here we have warps, and the memory consists of segments. Remember that segment size is 128 bytes. In here, the threads in the warp access to the different segments of the global memory. So this operation becomes serial. What is our target? What's our target? Our target is to force the thread in the same warp access to the same segment. The main target is to force the warps in threads in the warp access to the same segment. This is the idea. So, sorry, okay. Okay, before continue, I would like to tell you the example code here. We have two kernel. The first one named full coalesced access. That means the threads in the warp access to the same segments. So the load operation for a warp performs in one transaction in this example, because all the threads access to the same segment. So the loading operation performs in one transaction for a warp. In the second kernel, named non-coalesced access here. So we generate a random number between 0 and data size -1 and access to the global memory randomly. Here, each thread takes a random number, access to any location in the memory. So the threads in the same work will access to the different memory location of A and B, as you see. And in order to dominate the execution time, we iterate this operation, we perform this operation 100 times. So in this operation, as you see that we generate a random number between 0 and data size, and we use that one as an index for the thread, okay, and access to the memory location that is given by index. And loading the state of generator is as a coalesced way, so this does not affect the execution time. So this for loop and this operation dominates the execution time. Again, we have three arrays A, B, C, and we initialize them. We set the number of threads 1024 and so on. So in the second kernel, non-coalesced access kernel, the load operation of a work will perform at most 32 transactions. Since it accesses to the memory randomly, so the load operation for a work will perform at most 32 transactions. For the first kernel, full coalesced access kernel, it will be exactly one transaction. We use CUDA event record in order to measure the execution time of the kernels. We use XOR WoW generators in our code and so on. Okay, let me tell you the metrics that we used in the experiment. The first metric is number of global memory load operation. This is the total number of global memory load operation. The second one, GRD transactions per request metric, and it is the average number of global memory load transactions performed for each global memory load. So this gives us the average of the total global memory loads. Let's look at the output. And here, the execution time of full coalesced access is 9 times 10 over -6 seconds. The execution time of non-coalesced access is 0.0016 seconds, and the speed are around 177x when the data size is 2 over 15. Okay, and the data size is 2 over 15, speed up is around 177. It is important. Let's look at the results of metrics. Here, for the full coalesced access, the total number of global load transaction is 2048. 1024 is for loading A. Here, loading A. 1024 transaction is for loading B. And when we get their average, as you see that we get 1 because all of the global memory operations performs exactly one transaction. At most, not at most, exactly one transaction. So the average is 1. For the non-coalesced access, the total number of global load transactions is here around 60 million. And when we get the average here, we get 30.6. So as I told you before, the load operation of a work performs at most 32 transactions, and as you see that we get 30.6 transaction in average. So this shows us our code runs correctly, and we obtain proper output or expected output by checking the metrics here, by checking the information of the metrics. Okay, sorry. Now we set the data size to 2 over 22. 2 over 22, okay? So around 4 million data size. The execution time of full coalesced access is 0.00029 seconds, and the execution time of non-coalesced access is 0.51 seconds. There's a huge difference between them, and the speed up, as you see there, 1778. It's a very huge result. So coalesced access is very important in CUDA to the global memory. Let's look at the results of the metrics. GRD transactions is total number of global node transactions is here. 2 over 18, and the average is 1. That is the expected output. And for the non-coalesced access kernel, the average is here around 31.09. That is also the expected output for us. Okay. So how we can overcome this problem, or how we can handle it? So how we can overcome the non-coalesced access to the global memory? One of the approach is that we did in our study in the past is grouping. We used a similar idea in our study in the past. What does grouping mean? Here we define groups such that a group consists of contiguous segments. Okay, a group consists of contiguous segments or consecutive segments. And the number of segments in the group can be between 1 and 32. 32 is the verb size. So the number of segments, we can set the number of segments in a group. So it is a generic concept between 1 segment or 32 segments. If you set it to 1, that is similar to the full coalesced. If you set it to 32, that is similar to the non-coalesced. Now, so with this approach, now we are trying to force the thread in the same work to access to the same group. Not the same segment, now to access same group. Now our approach is to force the threads in the same work to access to the same group. Okay, let's examine our third kernel. We defined the third kernel about it, named semi-coalesced access. Now grouping is implemented in this example. Again, we have same arrays, 3 array. All of them are same, just we add group concepts in our implementation. So we can define the group size. Segment size is 128 bytes, don't remember. And we can set the group size. Group size is the number of data in a group, the number of elements or in a group. A group count is the number of groups in our approach. For example, we want that in this example, the number of segments in the group is 16. So each group consists of 16 segments. So the memory operations for a verb will perform at most 16 transactions. Since we have 16 different consecutive segments, so any memory access to that group will perform at most 16 transactions. And we implement it here. I will not mention in detail. We implement it here. First, we select a group here, pick a random group number, group ID. We pick a group ID. That means we pick a random group. Then inside the for loop, we select a random number within this group. So we select a random number or index to access within this group here. Then we access the threads access to the segments in that group. So the threads in the verb access to the selected segments, access to the segments of selected group, and it will perform at most 16 transactions. Okay, let's continue with the outputs. For the data size is 2/15. Here again, the execution time of full coalesced access is 9 times 10/16 seconds. For semi-coalesced access, where the the number of segments in the group is 16, the execution time is 0.00078. So we achieve 82x speed up with this approach. And the execution time of non-coalesced access kernel is 0.0016. So we achieve 174x speed up. Let's look at the output of the matrix. For the full coalesced access, again, the number of total global load transactions is 2048. Half of it for A, reading A, half of it is for reading B, and the average is 1, exactly 1. For the semi-coalesced access, the average is 13.4. This is also an expected output. It can be at most 16, so 13.4 is the proper output. And for the non-coalesced access, 30.6 is the average, so it is also the expected output for us. So when we examine the speed up, we can see the effects of eliminating the non-coalesced access is very important. And for the data size, where the size is toward 22, now the size is 22. Let's look at the execution time of full coalesced access. It is 0.00029 seconds. For semi-coalesced access, it is 0.22 seconds, and it achieves 757x speed up. And for the non-coalesced access kernel, it is 0.51, and the speed up is 767x. Of course, this speed up is about full coalesced access. the speed up of full coalesced access. This is the proper command on the result. So this speed up is speed up of fully coalesced access over semi-coalesced access, and this result is the speed up of full coalesced access over non-coalesced access. So if you make them with a full coalesced access to global memory, so we achieve these speed ups over the coalesced access versions or cases. So when we check the results of metrics, as you see, the average number of global load transaction is 1 for full coalesced, again 13.4 for semi-coalesced, and 31.09 for non-coalesced access. So we learned that this is an important concept while accessing to the global memory and for work concept. So we must be careful while we implement our algorithms. Any question? Any question? Chat. Sometimes I face some problems because of incompatibility of Ubuntu. Sometimes I cannot check the menu. Okay, let's continue. Okay, the second issue is warp divergence. This is also important issue on the execution time of our implementations. Some of the structures, such as if-else structure, are considered as a single instruction for a warp. It is considered as a single instruction. So that means a warp completes such instructions when all the threads in the warp complete those instructions. Like in the global load operation, all of the threads must complete in order that the warp complete such instructions. So in if-else structure, if the threads in a warp execute the different paths of if-else structure, executing these paths becomes serial. Okay, we have a if structure, if-else structure. PID is our global thread ID. If we take modulo of it and compare with 0, that means some of the threads execute the if part, some of the threads execute the else part in a warp. So in this example, the threads with even thread ID in a warp execute if part, path, and the remaining threads wait at that position. Then the threads with odd thread ID in a warp execute the else path, and the remaining threads wait in else position. Then the warp complete execute its instruction. So this operations becomes serial. So what is our target here? The target is make all the threads in a work execute same path in this structure. If they execute same path, the operations will not become serial. So how can we do it? Instead of using global thread ID, using warp ID is help us to overcome this problem. So here, instead of using thread ID here, checking threads, if we use warp ID, when we divide the global thread ID to the 32, we get the warp ID of the corresponding warp. So now we are using warp ID in the condition and make use modular here, modular 2. So in this example, the threads in a warp whose warp ID is even execute the if path. In other words, if the warp ID is even, the threads in that warp execute the if path. If the warp ID is odd, the threads in that warp execute the as path. So executing these paths do not become serial. Okay, let's examine our code here. We have two kernels, as you see. First one is no divergence implementation. Second one is warp divergence implementation. And we use if as if here, four condition here in our if as structure. And in each condition, one of the vector operation performs. Here in the first if, vector addition is performed. In the second one, vector subtraction is performed. In the third one, multiplication. In the fourth one, division is performed. It is similar in the second kernel. The operations are same, but the conditions are different. Be careful. In the no divergence case, we use warp ID. So these operate paths are distributed according to the warp ID. That means the first warp execute the vector addition, the second warp execute the subtraction, the third warp execute the multiplication, and the fourth warp execute the division, and so on. In our second kernel, we use thread ID. So the paths are distributed according to the thread ID. So that means the first thread in the warp execute addition, the second thread in the warp execute subtraction, the third thread in the warp execute multiplication, and the fourth thread in the warp execute vector division, and so on. And we run these operations 100 times in order that they dominate the execution time. And we have sufficient number of paths here, 4 paths. Memory operations are coalesced in both kernel. Memory operations are coalesced, so only the warp divergence dominates the execution time. There is no non-coalesced access here, so we can investigate the warp divergence performance or effect, warp divergence effect. Again, we use CUDA event record in order to measure the kernel execution time. Again, our number of threads in a block is 1024. Data size is 2 over 22. We call both kernels consecutively. Okay. First, let's check the execution time. Let's check the execution time. The execution time of non-divergence kernel is 0.012 second. And the execution time of warp divergence kernel is 0.038 seconds. So the speed up of non-divergence kernel is around 3. And let's look at the corresponding metric output. We use warp execution efficiency. It is the ratio of the average active threads per warp, ratio of the average active threads per warp to the maximum number of threads per warp supported on a multiprocessor here. To the ratio of average active threads per warp to the maximum number of threads per warp supported on a multiprocessor. And it is expressed as percentage. So the outputs are percentage. Here, in the no divergence version, it is 100 as we expected, because all of the threads in the warp active at the time, because either run if path or run as path. There is no divergence, so output is 100. But in the divergence version, divergence case, so some of the weights are weighed while executing one of the path. So some of the threads are idle. Because of that, this result is very low. 34% is very low output. So we investigate the effects of divergence here. Okay, now occupancy. The third issue is occupancy and streaming multiprocessor. Occupancy is the ratio of active warps to the maximum number of resident warps supported on a multiprocessor. This is important, is the ratio of active warps to the maximum number of resident warps supported on a. So that means tell us try to use the maximum number of resident warps, or try to make the warps active to the maximum number of resident warps. And it is related with the resource limitations of the streaming multiprocessor. As I told you before, here, these are the limitations. These are also important occupancy. These limitations are, at most, we can create, at most, 2048 threads can be active in a multiprocessor. This is the one limitation. Second one, we can create at most 1024 threads per block. And the third limitation is the maximum number of active blocks in streaming multiprocessor. It is 16. I told you before in the specification of TSK for the board. And another limitation is the size of shared memory or the number of registers. This is another limitation. You can check shared memory and number of registers by using this flag. So the main target in occupancy is to find the optimum number of threads in a block. in order to achieve maximum occupancy. So our target is to find the optimal number of threads in a block. This is the target in occupancy to achieve maximum occupancy. For example, if we set the number of threads in a block is 64. This is the number of threads in a block. Since we have since at most 16 verbs are active in a streaming multiprocessor, 16 blocks are active. Remember this limitation. Blocks, yes, if the number of block size is 64, when we multiply them, we get 1024 threads. So 1024 threads can be active at a time in an SMX, but the maximum number of threads that can be active in an SMX is 2048. So we only benefit half of it, right? Benefit from half of it, half of the maximum resident threads. So the theoretical occupancy is 100% here. So setting block size as 64 provides us 50% theoretical occupancy because of the limitations here. At most 16 blocks can be active in an SMX, and if the number of blocks is 64, at most 1024 threads can be active in an SMX, but the limit is 2048. So we benefit only 50% of theoretical occupancy. If we increase the block size to 128, and if we multiply it with 16 blocks, we achieve at most 2048 threads can be active. So we achieve 100% theoretical occupancy by increasing block size, as you see. And similarly, if you set the block size is 1024, since at most 2048 threads can be active in an SMX, only 2 blocks can be active in this case. But however, we achieve maximum limit of thread capacity in an SMX, so we achieve 100% theoretical occupancy again. So occupancy is related with the total number of threads that can be active in an SMX. Okay, okay. Let's examine our implementation again. Again, we use the same kernel with the previous example, vector at, and no divergence here, no divergence is occurred here, no memory coalesced access occurred here, so they do not dominate the execution time, and we increase the number of iterations of the for loop so that this operations dominates the execution time. Again, we have 3 host array, we have 3 GPU array, and we have number of threads. Okay, now we define 2 scenarios here in order to show you the occupancy and streaming multiprocessor efficiency of streaming multiprocessor. Okay, let me tell you the first scenario now. For different data size, we set the number of threads in a block to a different volume. In the first scenario, we set the number of threads in a block as the data size. Data size up to the data size is 2 over 11. I will show them in a table in the following slide. So in the first scenario, we set the number of threads in the block as the data size up to the 2 over 11, and at that point we set the number of threads in the block at 1024 because that is the maximum limit. In the second scenario, we set the number of threads in a block as 32 until the data size is 2 over 9. Until the data size is. After the data size is 2 over 9, we doubles the number of threads in a block as the data size doubles. Okay, we doubles it up to the 2 over 14. Up to the 2 over 14, then the number of threads will be constant because of the upper limit. Here, this is the picture of the scenario. The number of threads in a block, this is the column of number of threads in a block, and this is the number of blocks in a grid. This is theoretical occupancy. This is for second scenario. Here, when the data size is 32, the number of threads is 32. In the first scenario, as the number of data size doubles, the number of threads in a block doubles here until until the data size is 2 over 10. And from this point, the number of threads in a block remains same because of the maximum limit in the code. So let's look at the number of blocks. Here, the number of blocks is 1 up to the 2 over 11. Since we doubles the number of threads in a block as the data size doubles, the number of blocks remain same. When the data size is 2 over 11, since the number of threads will become constant, the number of blocks now increases. And here, the theoretical occupancy is related with the number of threads in a block. If the number of threads in a block is 32, we only use 1/4 of the resources in streaming multiprocessor. That means only 512 threads can be active in an SMX in a streaming multiprocessor. So we only benefit from 1/4 of the resources of streaming multiprocessor. When we doubles it, the theoretical occupancy also doubles as 50. Again, when the number of threads becomes 128, the theoretical occupancy becomes 100, and for the remaining one, it will remain same. And this first scenario achieves 100% theoretical occupancy when the data size is 128. Let's look at second scenario. In this scenario, for each data size at first, we set the number of threads to 32 up to the 2 over 9. 2 over 9, we set number of threads 32. Why? Because we are trying to distribute the number of blocks to the streaming multiprocessor efficiently. Remember that the blocks are assigned to streaming multiprocessors as much assign them evenly to the streaming multiprocessors. So in this scenario, as we increase the number of blocks, we are trying to distribute the blocks to the SMX evenly. For example, at the beginning, there are 1 blocks, only 1 block is assigned to 1 streaming multiprocessor, and then as it is increased, two of them, 2 blocks distribute to the streaming multiprocessor efficiently. For example, when the data size is 2 over 8, we have 8 blocks. So these 8 blocks are trying to distribute to streaming multiprocessor efficiently, and so we are trying to keep all the streaming processors busy with this approach. Let's check the theoretical occupancy of scenario 2. Here, since the number of threads is 32 up to the 2 over 9, the theoretical occupancy is percentage 25, as you see. When we double it and increase to 64, the theoretical occupancy increases the 50 percentage. When the number of threads is 128, the theoretical occupancy becomes 100. As you see that when the data size is 2 over 11, the theoretical occupancy of scenario 2 is 100%. But for the scenario 1, it achieves that value when the data size is 2 over 7. In terms of occupancy, okay, scenario 1 seems better, but in terms of efficiency, let's examine. Just I want to say, increasing the theoretical occupancy does not always mean a better time performance. So utilization of streaming multiprocessor efficiently is also an important issue for the better time performance. Sorry. So what is utilization of streaming processor efficiently? That means trying to keep all of the streaming processors busy. For example, when the data size here is 2 over 10, here 2 over 10, when the data size is 1024, the first scenario has only 1 block. The second scenario has 16 blocks. So in the first scenario, only 1 block is assigned to a streaming multiprocessor. So only 1 streaming multiprocessor is active. The remaining ones, the remaining 14 streaming multiprocessors are idle. This is not an efficient approach. This is not an expected way, but in scenario 2 here we have 16 blocks, so each block are assigned to each SMX, each stream multiprocessor efficiently. So all of the stream multiprocessors are busy in second scenario. So this is an important issue. We use two metric in the following example. The first one is SM efficiency metric. This is the percentage of time at least one warp is active on a multiprocessor, average over all multiprocessors on the GPU. So how can we obtain this percentage value? The ratios of the running time of each streaming processor to the total running time of the GPU is calculated first. Then the average of these ratios is the result of the metric. So we try to find the ratios of running time of each streaming multiprocessor to the total running time of your application. And then we have 15 ratios in total, since we have 15 streaming multiprocessor. So getting average them is the result of this metric. The result also is a percentage, or ratio. The second metric is sheet occupancy. It is the ratio of the average active warps per active cycle to the maximum number of warps supported on a multiprocessor. We will have an output between 0 and 1. If it is 1, that means we achieved 100 percentage occupancy. If it is 0, we achieve 0 occupancy. And achieved occupancy cannot exceed the theoretical occupancy. So the theoretical occupancy is an upper limit for achieved occupancy. Okay, let's examine the output, the result. I will show you in a table. These are the number of threads that for each scenario. This is data size. Then I will show you the number of blocks of both scenarios. Then SM efficiency, result of the SM efficiency metric, and the values of theoretical occupancy, the result of sheet occupancy, sheet occupancy metric, and the execution time of both scenarios. The values with yellow ones here, in these yellow ones, the parameters of both scenarios are exactly the same. So the result of both scenarios are exactly the same. I will not go over in detail. Just I will focus you to the green ones. Okay, let's focus to the green ones. Green ones means that scenario better than the other scenario for that metric. Okay, for example, in here SM efficiency, the second scenario is better than the first scenario when the data size is between 2/6 and between 2/13, right? As you see that the SM efficiency of second scenario increases because the number of blocks increases, as you see. But in the first scenario, the number of blocks is 1 until the data size is 2/11. So as you see that the SM efficiency of first scenario up to the 2/11 is very low, which is 6 here, very, very low. When I compare with S2, S2 is 78%, but S1 is because S1 has 1 block, but S2 has 16 blocks here when the data size is 2 over 10. So this is very important. Although the theoretical occupancy of S1 is 100% and S2 is 50, the SM efficiency is better than S1. For the yellow ones, as you see that the number of blocks are same, so the SM efficiency results are same because they are same, parameters are same. Let's look at the theoretical occupancy. S1 is better than S2, where the data size between 2 over 7 and 2 over 6 and 2 over 10. The theoretical occupancy is very low for S2. And let's look at the achieved occupancy. So the achieved occupancy, the S1 is better than S2, where the data size between 2 over 6 and 2 over 30. Achieved occupancy is better in S1. But our main output, our main comparison is about execution time, of course, because our main target is to achieve better execution time. So with S2, we achieve better execution time over S1 when the data size is between 2 over 8 and 2 over 13 here. So we achieve better time with S2. So this shows us that both theoretical and achieved occupancy does not always dominate the execution time. So having better achieved occupancy or theoretical occupancy does not always mean better execution time. Here, in this example, SM efficiency is more effective on the execution time of the kernels. So even though S1 has better occupancy, the execution times of S2 are better than S1 in some cases, as you see. This is the overall picture of this issue. Sometimes issue occupancy can be worse than the theoretical occupancy or is very low when compared with theoretical occupancy. There are some reasons about it. This can be unbalanced workload within blocks. That means the works in a block have unbalanced workload, or this can be unbalanced workload across blocks. So that means the blocks in a grid have unbalanced workload, or too few blocks launch. That means running few blocks in an SM streaming multiprocessor than the maximum active blocks per SM causes low achieved occupancy. And the last one, partial last wave can affect the result of achieved occupancy. And this is the website about these regions that you can find detailed information about these regions for low achieved occupancy. Okay, before starting optimizing parallel reduction, the last issue of this session, I will go over in the next lecture. Do you have any question? I would like to check it. Sorry. Sorry, I face a problem. Okay. Do you have any question? Okay, no question. Okay, let's have a lunch break. 1 hour, then continue at 2 p.m. Okay, thank you.